Hi, I'm Nick Cameron. I'm part of the Async Working Group, and in this talk, I'm going to talk about asynchronous programming in Rust. So, in particular, I want to kind of chart a course from how the current async system was designed, and in particular, like the design pressures that led to the design decisions that have led to where we are today, and some things that are good and some of the things that are not so good about the current system. I also want to talk about the work that the Async Working Group is doing to make things better and push us kind of into a shiny future where everything is great with async programming. So very quickly, just to kind of like fill you in on what you can do today if you're not aware. Async and await are keywords and they are stable. They've been stable since 2018. And so you can do asynchronous programming in Rust today. However, there is minimal support in the standard library for it, and frankly, kind of like the support of the language is somewhat minimal too. And we're really relying on the ecosystem to fill in a lot of the gaps there. But the Async Working Group is working, and we're trying to make things better. So let's go way back in time and think about how things were designed. So to reflect on some of these kind of design pressures, some of the requirements that led to the design, I want to think about what makes Rust unique, what makes Rust Rust. And I often come back to this kind of like fundamental trifecta of things we want Rust to achieve. So safety, super important. Performance and ergonomics, and you get to choose 3 in Rust. Okay, that's our real offering. So let's dig into that performance a little bit, because performance is really important. It's one of the big motivators for async programming. And performance can mean a lot of things in a lot of places. And we don't just care about making your program kind of like incrementally faster over what you could achieve in other languages. And we don't care just about kind of like the difference between an algorithm which takes kind of days versus minutes to run, right? We care potentially about every single byte of memory, every single cycle of the CPU. And we want to give you, the Rust programmer, precise control over what your program is doing, because you are the one who decides which bytes and which cycles actually matter. Okay. Now, a consequence of these kind of like, fundamental goals of Rust, we've got a few kind of design principles. The first one that often comes up is this idea of zero-cost abstractions. This is a design principle that we've inherited from C++. And this doesn't mean that your abstractions are free. That's not how it works. What it means is that if you don't use an abstraction, then you don't pay for it. And furthermore, if you do use it, it will be basically the same cost as if you had done a well-crafted version by hand. A similar-ish, is related to this idea of precise control of performance, is about this aversion to magic. You'll often hear kind of like people talking disparagingly about a proposed feature feeling too magical. And I think kind of like a better way to explain this idea is that if you want to have precise control over what your program is doing, you have to understand how the compiler is compiling your program, or at least be able to understand that at a high level. Another design principle, not so related to these others, but I think it's really important to understand where the design for async Rust came from, is this idea of providing the fundamentals. Rust is not about minimalism. There's a string abstraction in the standard library and a hash map, but we don't provide much more than the fundamentals. And in particular, we don't want to dictate to you like the high-level architecture of your program by having a really kind of like opinionated point of view on kind of like concurrency architectures or what have you. We somewhat deliberately leave that to the kind of like ecosystem, so that you can have kind of like libraries for things like actors, but you don't force everyone to use an actor model. Okay, so looking at the design, probably like the really most fundamental thing about designing an asynchronous programming system is whether you have a model based on green threads or on we call stackless coroutines. And these are both kind of jargony names. I'm going to explain both of these things. So green threads are like mini operating system threads. Okay, so the programming language provides a runtime, and this does everything that the operating system would do for operating system threads. So it's got a scheduler, it's got context switching, and so on. And this is fairly kind of like a heavyweight runtime. And the programming model for the programmer is pretty similar to using operating threads. You might have kind of like some kind of spawn construct, but other than that, there's very little syntactic overhead. And you basically pretend that you're using operating system threads, except things are a little bit more performant because you don't have to keep going through the operating system to context switch or what have you. The alternative is to build a system around kind of like async and await. This is the so-called coroutines model, where you have this syntactic overhead of async and await. The programmer is explicitly aware about these things, but they are compiled down to just regular machine code. And so at runtime, there's there's very little overhead, and we'll talk in a bit more detail about how that works, because this is obviously where we've ended up. Now, Rust back in the day, way before 1.0, Rust used to have a green threads model, but this didn't fit with those design principles that I talked about earlier. In particular, it was not a zero-cost abstraction, because everyone, if you're using green threads, then everyone is in this green threads world, right? And there's a lot of downsides to that. In particular, like the view that you have in your Rust code of what's a thread and how your programming is executing is very different from what other programming languages or what you would see from the point of view of another programming language or from the operating system. And that introduces a whole bunch of friction and therefore performance penalty when you are interacting between Rust and other programming and programs written in other languages. And furthermore, this mismatch between kind of like Rust's idea of a thread and everyone else's idea of a thread really becomes important with when you block the thread. And as a consequence of this, it's basically impossible to write like a high quality, low level IO library using the green threads model. And so the green thread system in Rust was ripped out before 1.0. And with the idea that kind of like we would later develop a system based around async await. And so I said that when we've got this async await system, that is compiled down into kind of like regular code. And in Rust, that regular code is futures. So a future is just a regular Rust data type, any data type, as long as it implements the future trait. And the future trait is pretty simple. It just has a single method, poll, and the user or the runtime makes progress by calling the poll function. So the future itself just totally inert, just a regular piece of data. And execution happens by repeatedly calling the poll function. And you can imagine that if you have multiple futures and a runtime schedules kind of execution by calling this poll function in sequence, then you get kind of concurrent but not parallel execution of these futures. Okay, so if that's how futures can give you this concurrency, how do we get from async and await to futures? Well, let's look at that translation. Let's start by looking at how we deal with the async keyword. So an async function is lowered to just a regular function that returns a future. And if we look at the type here, we use an impl trait type because we don't care what the precise type is. In fact, that precise type is kind of unknown other than to the compiler. But we do care that it implements this future trait. And that's all the impl trait type tells us. So that's perfect. Now, if we actually think about like the semantics of this, when we call an async function, we're just going to get a future back. And as I said, a future is just a totally inert piece of data. And that's why you have to await or poll that future to actually make progress, which can be a bit surprising if you're used to kind of like async functions in other languages, which start making progress as soon as you call them. Now, if you can have async functions, it's like a natural step to then want to have async methods and traits. And unfortunately, this is not supported in Rust at the moment, and it's one of the like most kind of like in-demand features, right? So I'll try and explain why this is trickier than regular async functions. So let's look at that that translation step. So we would just do the same translation, and the semantics of returning a future is super easy. But the type here, well, the type is we've got this impl trait type on a trait method. And unfortunately, that's not supported in Rust. This feature is called return position impl trait in trait. And I'm not even going to try and pronounce that acronym because only a frog could do that. But the good news is that this feature, like implementation of this feature is way underway. There's like lots of the parts of it in the compiler, which is what we care about for async functions, for async methods. And this is going to be available to use for everybody pretty soon, I hope. Now, the way that return position impl trait and trait is implemented is that the return type becomes an associated type. And this is really important because this means that different implementations of the trait can have different concrete types for the async function. And that allows you to have different implementations, which after all is the whole point of having like a trait in the first place. So that's really important. There's a wrinkle here in that if you have a generic function, or you use a lifetime from self or one of the other arguments in the future, and this is super common without you really noticing in async functions, then you need the generic associated type, which we abbreviate as GATs. And again, this is another feature that's not fully implemented. This one's a little bit further ahead. You can actually use this on unstable Rust, and we're talking about stabilization at the moment. What's important for the async features, async methods work is that it is implemented in the compiler. So with these two features, return position impl trait and trait, and generic associated types, we're really close to being able to support asynchronous functions in asynchronous methods and traits. And so that's something that should ship in the very near future. It gets even more complicated than that because we often want to call asynchronous functions on trait objects, and that is not something that would be supported with this translation. So the working group is looking at doing that. I won't dive into the details here, but that work's underway too. Okay, so we've talked about translating async. How about await? Await is a little bit more complicated. I'm going to go into that in depth in this talk. Await is a signal to the compiler that you can split the function here into futures, and then you can stitch all those futures together into a state machine, and the asynchronous runtime can then poll that state machine to make progress, and in turn that's going to poll these individual futures, which where the future here will probably come from being an asynchronous function. As I said, it's a bit complicated. We don't need to kind of like understand this in depth. What's important is that it's a future that's being awaited. And one thing that the asynchronous working group has looked at is making that more flexible. And the way we do that is with an into future trait. So I want to talk by analogy about into iterator first. So into iterator is a trait that says this is a data type that is iteratable, and here's a way to get an iterator over it. And this is implemented by things like vec, by borrowed slice, by many collections. And it's used in the implementation of the for loop. So when you write a for loop like this, the thing that you can kind of iterate over in the for loop doesn't have to be an iterator. It can be like anything that's iteratable by using an iterator. And trivially, that includes iterators themselves, right? But it also includes vecs and slices and so on and so forth. And it's the same thing with futures. We have this into future trait now, which is anything that can be converted into a future. And now when we call await, it doesn't have to be a future on the left-hand side of that. It can be anything that can be converted into a future. And this makes a number of programming patterns just a bit more ergonomic. So here's an example of using an async builder. So like the kind of really common builder pattern, this is a replacement for kind of complicated constructors where we call kind of like property methods to initialize the builder. And the nice thing here is that we can then just await the builder itself. We don't need to have kind of an explicit step to convert it into a future before we await it. Okay, so just kind of like changing tack a little bit now. So we talked about how we go from async functions to futures, and then we poll the future to make progress. Okay, and after we've polled it a few times, the future will hopefully make progress and return a result to the caller of the future. What happens if you just stop polling? In particular, if you poll a future, or even don't poll it at all, you just drop it, or you poll it for a bit and then drop it, then, as I said before, this is just an inert data type. There's no execution that's going to carry on. The future is cancelled. And cancellation is a really useful thing to do. And in fact, like having cancellation so easily like linked to drop is really nice as well, because it means you never need to worry about like zombie futures who are just progressing in the background with no way for you to get the result of them. And we make use of this in features like the select macro, which is going to drop futures that we don't care about and to cancel them. And that's really kind of like a clean way for it to tidy up these futures. But it comes with some problems too. And again, these can be somewhat surprising, especially if you're used to asynchronous programming in other language. So consider a future which, when it's polled, it is going to make some progress, and it's going to write that progress to an internal buffer. And when it's made enough progress, when it's done, it's going to return the contents of that buffer to the user. Well, this is fine. This is kind of a use case you can imagine to futures. It's a perfectly great thing to do, unless that future gets cancelled. And if the future gets cancelled, then this data we've written into the intermediate buffer is just going to be lost, gone. And data loss is generally pretty bad. You generally want to avoid this. So you have to be really careful. And so you have to reason about this idea of kind of like cancellation safety for your futures. Is this a future that can get cancelled? Is something bad going to happen if it does get cancelled, and so forth? And this is a bit of a foot gun for asynchronous programmers. And it's something the working group has spent a lot of time kind of thinking, can we do better? And another place that this idea of cancellation causes issues is with completion I/O. So this is about designing the async I/O traits. So that's kind of like async read, async write traits. And completion I/O it's kind of the new hotness at the moment, because IOUring on Linux uses a completion model and is pretty awesome. Less fashionably, it's also the default way to do asynchronous I/O on Windows using IOCP. The way completion I/O works is pretty intuitive, actually. So the user initiates a read with some call to kind of like into the operating system, and you pass in a buffer to the operating system. And then the user can get on with something else, right? It's asynchronous I/O after all. And at some point further on in time, the I/O is going to be done, and the OS somehow notifies the user that the I/O is complete. And at that point, the user can look at its buffer, and lo and behold, the data will be there to read. Now, there's some interesting invariants about this buffer. Okay, so the buffer is supplied by the user, but the user must guarantee that that buffer stays alive and that the OS has unique access to that buffer for the entire duration of that I/O. Right? Now, this actually fits really well with kind of some of the core concepts of kind of like borrowing in Rust and wrapping all that stuff up in an async function. So the way that this would work in Rust is that you've got your buffer here. We're just going to allocate it locally on the stack, and then you call read, and you're going to pass a mutable reference to that buffer, and that's unique. And then you're going to await the result. And Rust guarantees that buffer is not going to be used by anyone else, and it guarantees that it's going to live until after that read call completes. So this is fantastic. This just very naturally maps onto this like quite kind of like subtle invariant that completion I/O requires. Unfortunately, it doesn't work so well in the presence of cancellation. So if we take the future, remember this asynchronous function is just returning a future, and we just drop it, or even worse, we call memForget. And yeah, this is a silly thing to do, but it's probably actually wrapped up in a select macro or something similar to that. So this does actually happen in real life. Well, what happens now? What happens is that the future is cancelled, which means it's dropped, which means that the buffer is deallocated. And that's safe to do because we've reached we're never going to call the poll function that's underlying these things again. So that buffer's never going to get used. Unfortunately, the operating system doesn't know that the read has been cancelled. As far as the operating system is concerned, we still want that I/O to happen, and it still thinks it has unique access to that buffer. And so it's going to read into that buffer, and that's going to be a use after free error. And we hate those in Rust. We try really hard not to have use after free errors. All right, well, why can't you just cancel the read with the operating system? And you can do that. Most completion systems allow you some way to cancel the I/O. Unfortunately, cancellation is asynchronous too. And the invariant around cancellation is that you have to ensure that buffer lives until either the cancellation or the original read completes. Okay, and we can't do that, right? We don't have kind of any facility for calling an asynchronous function when a future gets cancelled. Okay, well, what about having async drop? Would that solve the problem? Well, for one thing, async drop turns out to be really complicated. Although it's kind of simple to explain, that it's kind of complicated to design. And I don't have time to go into that, which is a shame because it's really interesting. But it's something the Async Working Group has been discussing and thinking about. I'm hopeful that we will actually have an async drop implemented at some point. It's just not as easy as it sounds. But even if it were, or even if we did put all that effort in and got that kind of like soon, the more fundamental problem is that in Rust, destructors are not guaranteed to get run. So it's okay to rely on destructors running most of the time because most of the time they run. But in this case, we'd be relying on destructors for soundness, and that's not okay. This would, because you can call memForget, or just destroy the memory by in other ways, you can't guarantee that the destructor is going to be run, and in those cases you would still have this use after free error. So unfortunately, calling drop, whether that's async or synchronous, is not a solution. We do have solutions though. The simplest is that the I/O library manages a buffer, and you just copy into the user's buffer. And although that's simple, which is good, it's also not very performant. And worse, it doesn't fit in with this idea of having precise control over the performance, because the IO library is managing the buffer and this copy is forced upon you. And really, like, one of the main advantages of using completion IO is this idea of having 0 copies. So that works, but it's not great. A better approach is perhaps using the buff read trait. Now, we usually think of buff read in terms of having a buffer where we kind of collate multiple small reads before returning the whole thing. But that's not what's important here. What's important here is that that buffer is internal to the reader, right? And in this case, that would mean the IO library can manage that buffer, and then the caller can read that without that copy being forced upon them. But this is fine in a lot of cases, but sometimes you might want to read directly into the user's buffer, or you don't want the buffer to be managed by the IO library. And in this kind of case, we might need a new trait like owned read. And the idea here is we'd pass an owned buffer to the IO library rather than a borrowed one. So imagine something like a vec of U8 rather than a borrowed slice of U8. And so now the caller is responsible for the buffer management, and we just pass it to the IO library, so the IO library can keep that buffer alive just for long enough for that call. So we're not exactly sure what the eventual solution here is going to look like. Perhaps we'll have support both of these traits, but we are confident that we'll have some kind of optimal way to support completion IO. All right, I want to finish this talk off just to summarize what I've talked about, in particular where we're going, and give you an idea of the kind of like shiny future we're heading towards, hopefully. So we want you to be able to write async anywhere you can write a function. So whether that's methods on traits, whether that's closures, whether that's destructors, we want async to be everywhere. And it shouldn't matter which runtime you use. There's always going to be like reasons for different users to want to use different runtimes, but you should still have access to the entire ecosystem and all the goodness of programming with asynchronous Rust. Okay, and in particular, if your requirements, your constraints change, it should be easy to change runtime too. And when for somebody who's starting programming in asynchronous Rust, you should be able to get started without having to care about which runtime you use, without having to do that research into finding the right one for you and depending on a great big runtime from the ecosystem. And once you've made your program, inevitably there are going to be bugs in it, and finding those using a debugger should be a great experience. In particular, it should be, work just as well as using a debugger with synchronous Rust. And I haven't had a chance to talk about that much in this talk, but the Async Working Group has been doing work on that too, to work towards having a great debugging experience. And we want programming with async Rust to be easier. We've been doing a lot of work thinking about the invariants, the guarantees that you should have when doing asynchronous programming, and especially around the life cycle of features, like how they're started, how they end, whether they're cancelled. And we want to kind of like use that to design libraries, perhaps in the ecosystem, perhaps in the standard library, and come up with design patterns which enable you to write asynchronous Rust code more safely and more easily. And to achieve all this, we need your help. So this is our call for contribution. And of course, there's a ton of work to be done. If you would like to contribute to the design work, to the implementation, documentation, testing, we would love you to help out. But in particular, even if you don't want to do that work, but you are using async Rust today, and especially if you are implementing a runtime, whether that's a general purpose runtime that's available for everyone, or whether that's specific to your project, and perhaps that's kind of like a closed source, and so we don't know about it, then we really want to hear about your experiences and your opinions on the work we're doing, so that we ensure that we're building the right thing to help you continue to build asynchronous Rust programs and to do that kind of better. So we work as much as we can in the open. We do a lot of work on GitHub, and the WG Async repo is a great place to start. For more synchronous communication, we use the Rustlang Zurip chat, and then we have the WG Async channel there where we communicate. So please reach out to us in either of those places. I'm Nick Cameron on Zurip, and I'm Nick_R Cameron on Twitter, and I'm going to be on the RustConf Discord. Well, right now, and for some time after the talk. So please reach out either on Discord or Zurip or Twitter if there's anything in this talk you want to talk about or that's interesting, or if you want to just follow along to see where this goes. So that's the end of the talk. Just thank you for listening. Cheers.